All right, my friends, let's take a look. I do want to take a couple minutes and make sure that not only can you kind of, regurgitate these, you have them memorized, but you actually have maybe a little respect for them at the same time. I think it's a lot easier to remember math if you have a little respect for it. So, let's start with the Pythagorean identities. The most basic of the Pythagorean identities, this is the one for sine and cosine. I like to just kind of think about the unit circle for an explanation for that. So let's say this is a unit circle. Let's say that's a beautiful circle. Anyway, if you have any point xy that's on that circle, um, I hope it makes sense that the relationship between x and y, since it is on this circle, here's x, here's y, here's 1, would be that x squared plus y squared equals 1. And then furthermore, since cosine of angle theta, I'm going to put theta there as your central angle. Since cosine of theta is equal to adjacent over hypotenuse, if you're on the unit circle, cosine is just your x coordinate. And similarly, sine of theta is opposite over adjacent, which is why the sine is just y on the unit circle. So if you were to take this trig and put it in to that relationship between x and y, instead of x squared, you'd have cosine squared theta, and instead of y squared, you'd have sine squared theta, and that's always guaranteed to equal 1. So I'm just going to go ahead and copy that in as the first of the Pythagorean identities. Um, Similarly, if you were to, let's say you were to start with this identity here, if you were to just divide both sides by cosine squared theta, then you'd have one of the other Pythagorean identities. So cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared, tangent squared, and 1 over cosine squared is equal to secant squared. There you go. And then the last one, the last Pythagorean identity, is also a direct ripoff of the original, where you could just divide both sides by sine squared instead of cosine squared. There we go. So cosine squared over sine squared is cotangent squared theta. Sine squared over itself is 1, and 1 over sine squared is cosecant squared theta. There you go. Okay. So now that we've got those established, let's move on to double angle formulas for cosine. To explain these, so these are, we didn't use those as much as the other ones last year in pre-cal. So let's see. If you didn't remember these, then could you remember the sum formula for cosine? That is equal to cosine of your first angle times cosine of your second angle minus sine of your first angle times sine of your second angle. And then if you can remember that, then what if u and v were both x? Then what would the expanded side be in the sum formula? Well, it would say cosine of x times cosine of x minus sine of x times sine of x. And then if we simplify both sides, on the left side, you'd have cosine of 2x. And on the right side, you'd have cosine squared x minus sine squared x. There we go. And, what I'm showing you here was all the rage last year in chapter 5 in pre-cal, but just because it made sense back then doesn't mean that it especially makes sense again today. So I just wanted to remind you of these things. Okay, now let's say you want to know what cosine of 2x is, but you don't want to have to know what cosine and sine are, which you'd have to know for this formula. So what could you do to get, let's say you only know cosine and you want to know cosine of 2x. Well, you could just do a Pythagorean swap on sine squared. You could replace that with 1 minus cosine squared x. And then combine like terms, and you'd end up with 2 cosine squared x minus 1 when you simplify it. There we go. And that's the double angle formula for cosine in terms of cosine. There we go. And before we talk about the other double angle formula, Let's actually show how you get the power reducing formula for cosine. It's just a direct ripoff of this formula here, where all they did was they solved for cosine squared. So they added 1 over, and then they divided the result by 2 to algebraically solve for cosine squared. There you go. And so that is a formula that we'll start reaching for. That if you have like cosine squared, like let's say in an integral, and you don't like having cosine squared in an integral, you could replace it with this version of it. And what's nice about that is you don't have cosine squared anymore. It would make it, it would take it from an integral that's undoable into an integral that's doable. So there you go. All right, let's go back. Let's go back to double angle formula for cosine in terms of sine. So that would be a direct ripoff of this double angle formula. So I'm just going to copy it. So let's say you want this to be all in terms of sine. You could swap cosine squared out for 1 minus sine squared. Bring the rest down. And you'd end up with cosine of 2x is equivalent to 1 minus 2 sine squared x. And then we just have to solve for sine squared. So to do that, up to you, you could add 2 sine squared x over, and then subtract cosine 2x over, and then divide both sides by 2. And then you'd have it. So let's see. So you'd have sine. So this is the power reducing formula for sine. So you'd have sine squared x is equal to 1 minus cosine of 2x all over 2. And to back up, that came from the double angle formula for cosine in terms of sine. There we go. Okay. So hopefully you feel very comfortable with all of the identities that we have here, and it would be in your best interest to memorize them if you didn't already have them memorized before we continue. So even if you need to pause the video, it would be worth your time to do so. It would kind of reduce the frustration and totally be worth the trade-off in time. All right. So with that said, I would like for you to take at least maybe a couple minutes, I'd say between 2 to 4 minutes on example 1, poke it with a stick, see if you can figure it out, and then check in with me in the next video. Good luck.